In this video, we are going to look at some of the basic shapes of the main block elements. So this is mostly a review of what we did in honors chemistry, but I think a good way to get a start and look back at it. So in this valence shell electron pair repulsion support packet, or VSEPR support packet, I think on page 3, I have this shape guide. And I could look at family 1, which would be the alkaline metals. I'm just going to ignore that. Those are typically going to be ionic substances, so it's not really relevant. In fact, family 2A, with the exception of beryllium, is pretty much ionic substances too. It's not really relevant except for with beryllium, so we should take a look. And then there's some applications from that too. So let's say I have two things attached to something. What's going to happen is valence shell electron pair repulsion. Electrons repel each other. So they're going to try to get as far apart from each other as possible. So family 2, if I take a beryllium and either put two H's on it or two F's or two Cl's or something, it's going to look like this. It's going to be a linear molecule with the two H's or two Cl's or whatever as far apart as possible. In this case, 180 degrees in a linear thing like this. So essentially there's two bonds here. There's no unbonded electron pairs. It's 180 degrees. Now, what would happen? Let's say you have, let's say it's BCl2, BeCl2. You're going to have a dipole toward one chlorine. You'd have a dipole toward the other chlorine. Would those dipoles cancel? Yes. So if dipoles cancel, even if you have two polar components, they will cancel out and make this molecule nonpolar. There's something called hybridization. There's two bond sites, okay? And so we would actually say this is SP2. You get two letters for that. We'll probably talk about that more in discussion. I have another molecule like that where you get to double bonds, and it might be kind of hard to see this, but there's a carbon in the center and a double bond to an oxygen, double bond to an oxygen. This is also going to be a linear molecule with SP hybridization, and it is nonpolar because there's a dipole going toward one oxygen, dipole going toward another one. So you can see that there. So even though we're only using this shape as beryllium for family 2, because the others will be ionic, magnesium below, you can see how it applies when there becomes multiple bonds, and you can get a linear shape here, and it fits that model. Okay, family 3, again, most of the things are metals and they're going to be below. Beryllium is a metalloid, but we can think of it as a non-metal and having covalent bonds. It would look like this, the B with the three H's, or if you had Cl's or whatever attached, it's going to be planar, it's going to be flat. I don't know if you can see that here, but in the center would be the boron and either three H's or three Cl's or whatever you decided to attach to it. Okay, there's three bonds, there's no unbonded electron pairs, and if it's planar and it's flat, 360 divided by 3 would be 120-degree bond angles. Now, even if I had like Cl, even if I had polar covalent bonds, what's going to happen is the dipoles would cancel, and overall this molecule would be nonpolar, assuming I had the same thing attached to each one. Now, if I put chlorine on one and fluorine on another, then it's going to lean toward the more electronegative element. Okay, and there are three what we call electron domains or bond sites. So we're going to have three letters, and we're going to call the hybridization SP2. All right, now I'm going to go to my tetrahedron, which is CH4. And I'm thinking, oh, why wouldn't this be 90-degree bond angles? Well, by forming a tetrahedron, things can spread out further. I don't know if you can see that right here. This might be a better structure to show this. So I have the black carbon right here, and then I got the four yellow hydrogens right here. So what's going to happen is this isn't flat right here. There's a bottom between my hand and these yellow things, and there's some airspace between there, and then there's one on top. And I can flip this around. It actually is very symmetrical. There's always going to be like a tripod on the bottom and one on top. This is a tetrahedral shape. If you look at this, it's a little bit harder to count them up in 3D, but there's 1, 2, 3, 4 yellow things, and that's going to give me 1, 2, 3, 4 bonds. Okay, by going into 3 dimensions, it spreads the electrons out further, so it's not 90 degrees, it's 109.5. And even if these were polar bonds, let's say I put F on every one of these things and I had polar CF bonds, the overall thing would be non-polar because the dipoles would cancel. Now, let's say I just put one F on or two Fs on, then it's going to be more polar toward the more electronegative thing. So you got to be careful with it. There's 4 bond sites, so I get 4 letters. We're going to call this sp3 hybridization right here. But this is carbon. We always think carbon bonded 4 times, and you get that tetrahedral 109 degree 0.5 bond angle right there. Okay, I'm going to go to NH3, which I have a model like this with an N on top and 3 hydrogens. How does it compare to like the BH3 right this one's more 3-dimensional. This one here is flat. I don't know if you can see that. This one's more 3-dimensional. You might not be able to see that. I could draw the structure here. Again, there is a gap. The blue one is a little bit higher up than the yellow ones. Okay, so there's definitely a gap. I'm trying to put something there and show that. I don't know if I can. I put this cardboard here. Let's see if you can see that. Not really. There's a gap when I put that in there. I think you can see that the blue one's elevated from the yellow ones when I put it on a flat surface. Trying to give you a picture of that. Okay, so really this structure, if I think about this like the CH4, it's the same thing, but what happened is I have 5 valence electrons in nitrogen, so I have 3 bonds, and then I have an unbonded electron pair that's just sitting at the top. So we call this shape, we don't really see the unbonded electron pair, so we're going to call it trigonal pyramidal as opposed to trigonal planar because there is that 3-dimensional effect. It's not a flat structure anymore. So I look at this, it has 3 bonds, and then I just left the stick in. It has 1 unbonded electron pair right up there. So 3 bonds to hydrogen, 1 unbonded electron pair. The electron pair takes up a little bit extra room. Since its electrons spread out instead of being directed toward another atom, it takes up a little bit more space and it squeezes the bond angles of other things just under 109.5. Okay, now let's say we have polar bonds. Okay, like ammonia has polar bonds. Okay, there's electronegativity difference. These dipoles do not cancel out. Okay, it's going to be more negative toward the nitrogen. So you get a push toward the nitrogen's pulling electrons, the nitrogen's pulling electrons, the nitrogen's pulling electrons. So it's more negative here where this electron pair is on top, less negative on the bottom if I have NH3. So this would be a polar molecule. It would still be sp3 because we count electron domains where they're either bonded 1, 2, 3, or unbonded electron pairs still count as an electron domain. So 4 electron domains, it's still hybridization is sp3. Okay, so that's this one right here. Let's say I go to H2O, which is in family 6. It's like taking this NH3 and taking another electron pair off. Okay, so now essentially, whether they're bonded or unbonded electron pairs, they're going to try to get as far apart as possible. So it's still taking that tetrahedron shape, except I have 2 unbonded electron pairs. So not looking at the electron pairs, even though it's taking part of the shape, is I see, hey, this looks like it's bent. Okay, so the shape is bent. Sometimes they'll say angular, but that's all that we can really say for that one. This one does have 2 unbonded electron pairs and 2 bonded electron, 2 things bonded to the hydrogens in this case, if we have water. The unbonded electron pairs take up extra space, so it squeezes this bond even tighter, 104.5 for water. It is polar covalent. We talk about water having a negative and positive end. It's more negative by the oxygen, more positive by the hydrogen. Okay, sometimes we show it like this with a little red one for oxygen instead, but you don't see the electron pairs of this model, but you see the nice shape that we have for H2O. This is the same type of structure right here, just showing these electron pairs right there. Okay, there's still 4 electron domain, 2 bonded, 2 unbonded, so it still is sp3 hybridization, and that's typical of your family 6. Okay, family 7, we go back to a linear molecule. If I look at, and I don't know if I have a picture of this, but there's just 2 points. If I look at fluorine has 7 valence electrons, it could pick up 1. That would be linear. So you have 1 unbonded. I guess you could look at this structure and just say, what's the shape of it? If I do this, well, there's just 2 points, but there's 3 unbonded electron pairs. So this would be, you can't really have a bond angle with that. And I'm not worried about the ionic or covalent so much. Depending what you have attached to this, it's definitely going to be one's more polar than the other one. So it's going to be more negative toward this end, more positive toward the hydrogen in this case. And that is going to still be sp3, 3 unbonded electron pairs, and 1 bonded pair of electrons right there. Okay, so that's kind of and then the noble gases, family 8, won't react with everything. So we're primarily looking at families 4, 5, 6, and 7 when we do the covalent bonds, but we'll see some applications where we go into 3 and 2 with beryllium and boron, and then some of the double bonded or triple bonded structure, we'll see these shapes as well. And really with the metals, okay, that are here or in families 2 and 3, we're more thinking of ionic substances there. So this is kind of an overview of the shape guides, give you a little visual of those things. And hopefully that helps out in seeing these molecules in 3D. Thank you.